My name is Gavin Brown, and I'm going to talk to you today about memorization of training data in machine learning. This is joint work with Mark Bunn, Vitaly Feldman, Adam Smith, and Kunal Talwar. Now, machine learning models contain information about their training data. Our result is a very strong version of this statement. Informally, we give natural settings where memorization of almost entire examples is necessary, no matter the learning algorithm that's used, and even when many of the details that are memorized are irrelevant to the task at hand. Now, memorization is sometimes an explicit part of the training process. For instance, the model in the famous k-nearest neighbors classifier is just a description of the data set. But memorization can sometimes happen even when it's not intended. Recent work by Nicholas Carlini and a large group of authors showed that OpenAI's GPT-2 model has memorized huge amounts of training data verbatim, including people's personal information like emails and phone numbers. This is very concerning from a privacy perspective, but also fascinating. Why is it that this model, that's such a good generator of English text, has memorized information that seems actually irrelevant to the task that it's trained on? Before I get any further, I want to mention that memorization of training examples is distinct from the phenomenon of memorizing training labels, which has been studied a lot in the literature. Most relevant is recent work by my collaborator, Vitaly Feldman, who showed that there are natural tasks where any accurate classifier must memorize the labels. Our work is about the training data, the actual examples themselves, showing that accurate models must encode the data on the tasks we consider. To describe our results, I need to describe our learning setup. We'll have a data set X, which will be n rows drawn IID from some distribution P. The data will be binary and we'll have D bits per row. We're doing classification, so we'll have binary or multi-class labels. And we'll take our data and feed it to a learning algorithm, which will output a classifier M. I want to emphasize that we assume nothing about this learning algorithm. In particular, it may be distributed or in a federated setting. Our central question is, what does the classifier M tell us about the data set X? I need to make a minor tweak to the setup and say that actually we'll be drawing the distribution P from some prior or meta distribution Q. We'll call Q the learning task, and it'll be known to the learning algorithm, but the actual distribution over labeled examples, P, will be a priori unknown to the learning algorithm. For each task, there is a Bayes optimal learner, which minimizes the misclassification error, but necessarily exposes a huge amount of information about its training data. We will compare the accuracy of the learning algorithm to the accuracy of this Bayes optimal classifier. Our main result is that there exists tasks Q for which every data set X has a large subset S, such that the entropy of S is big omega of n times d with high probability. This means that the subset is large and contains a lot of information. And furthermore, that for all learning algorithms, if the error of the classifier is within some epsilon of optimal, then the mutual information between this special subset S and the classifier, even conditioned on the distribution P, is at least the entropy in the special subset times some 1 over 1 minus f of epsilon, where f of epsilon goes to 0 as epsilon goes to 0. Now, this 1 minus f of epsilon captures the fact that as you approach the optimal accuracy, the learner must reveal all the information about these special examples. You must memorize entire examples. And the fact that we're conditioning on P means that the classifier conveys a large amount of information about this special subset, even to an observer who knows the underlying distribution. That means that it's conveying a large amount of irrelevant information, things that are useless for the task. In our setting, this shows up as noise or irrelevant features. In particular, this lower bound on mutual information implies that the model itself must be large to convey this much information, a constant fraction of the size of the data set. In the learning problems we consider, the distribution will be a mixture of many subpopulations, each with its own rules or label. Our tasks, which I won't have time to describe in detail, stylize sequence prediction or next symbol prediction, and any kind of multi-class high-dimensional labeling problems such as image labeling. Now, when we draw data points from a mixture over clusters, some of the subpopulations will receive many data points, some will receive none, and some of them will receive exactly one. And these data points we call the singletons, the sole representative of their subpopulation. We established a series of reductions showing that if your learning algorithm is accurate overall, then it must be accurate on the singleton subpopulations because there's many of them. And this implies that you must reveal near complete information about these singletons. For this last step, we prove new information complexity lower bounds. Now, our lower bounds are in terms of mutual information and don't immediately apply anything about recovering the data from a model. So to supplement our theorems, we conduct some experiments on synthetic data sets. We generate these data sets from distributions used exactly in our proofs. And we train logistic regression and multi-layer perceptron, just a single hidden layer feed-forward neural network. We train them to high accuracy on these data sets using gradient descent. We then give an adversary query access and ask them to try and recover the singletons from the model. We find that a simple adversary is able to recover almost perfectly from the logistic regression, usually able to recover all the data points exactly. And for the multi-layer perceptron, we find that an adversary is able to recover on average over 98% of the singleton's bits, an overwhelming majority of the bits exactly from the data. We can visualize these results by looking at this plot, which shows on the x-axis the gradient steps over the training process, and on the y-axis the errors that have been rescaled to live on the same axis. And we see that the train error in blue and the test set error in yellow start out high and do some crazy things, but eventually go down towards zero. But as the training process goes on, the attack error gets better and better. After each gradient step, the attacker is a little bit more successful until eventually they're able to recover almost over 98% of the singleton's bits from the data, of these special data points that are the sole representative of their subpopulation. In conclusion, our results suggest that giant models might somehow be unavoidable. The GPT-3 model takes 300 gigabytes to store. And this might be because it really needs to encode individual inputs in its, for high accuracy. We saw experiments how we're able to recover data even from simple models, such as logistic regression in a one hidden layer neural network. Our work also suggests new ways in which privacy might be hard. It might be that it's underrepresented subpopulations, the places where the data is scarcest, which are at the highest risk for exposure, because these are the places where the model stands to gain the most from memorization. And it's possible that this behavior is exacerbated in the federated setting. Our lower bounds apply to an algorithm that can see the whole data set at once. But of course, we know when the data set is distributed, this is a significant constraint on the learning algorithm. Finally, I want to leave you with reasons for optimism. In our setting, the hard distribution is tailored to the sample size. But if you fix the task and let the sample size grow to infinity, then the level of memorization required decreases, eventually approaching zero. With that, I'd like to thank you for listening to my talk, and I look forward to speaking with you at the conference, at the workshop.